Okay, so again, it's been a while since we've had a lecture like this, just to sort of remind you guys of sort of where we are and what we're doing. I'm trying to give you guys a sort of historical perspective on synthesis and how things have sort of changed over. Come on, Rick. um, how synthesis certainly evolved and some of the driving forces behind different syntheses and some of the strategies behind certain methods and different syntheses. And so again, we've discussed some of the chemistry of Woodward and sort of the birth of modern synthesis. And by and large, everything that I'm going to be discussing after today is going to sort of be cloaked within a specific framework, and I'll discuss multiple people. But today I sort of wanted to give a full day to E.J. Corey, and talk about a couple of his syntheses. And so most of you guys have heard about E.J. Corey. Certainly when I think of E.J. Corey, again, when we were doing our name reactions, right, we had all these Corey syntheses, Corey whatever, Corey, all these different name reactions that he's done. And so I think when I think of Corey, I sort of think of sort of retrosynthetic analysis, right, which is a strategy, and we'll talk about that a little bit today. And the other thing that I think is sort of something that's a hallmark of Corey syntheses within that sort of retrosynthetic framework is let's come up with the best way, let's strategize the best way that I think I can come up with a target, and then let's see if we can make it. And that's going to involve sort of really testing some of the limitations, figuring out what the limitations of our current technology is, and then trying to develop new chemical methods that can sort of overcome that. And certainly there's people that do that nowadays, but I would say more than not, it's sort of the other way around. It's sort of you come up with a synthetic method, and then you try to, in total synthesis, and we'll discuss some of this, and you come up with a synthesis that would actually highlight that method you come up with. I think Corey, one of Corey's real hallmarks, and we'll sort of discuss that as well today if we have time, is, let's come up with a synthesis, and then let's evaluate it, and let's look at some of the real things that aren't so good with that synthesis, and let's develop new chemistry that can hopefully overcome those limitations. And so, so again, the two syntheses that we're going to discuss today are longifoline, which is was the actual natural product in the paper. Synthesis of longifoline was actually the first one where Corey sort of started discussing retrosynthetic analysis. And so I'll just discuss a little bit of his discussion on that. And then we'll go through the synthesis of it. So what you'll see is we'll talk about how, so the reason I'm using red is that it seemed like it was the one that looked the best on my monitor. So, so if it's painful for your eyes, I apologize. But longifoline is a rather, 1, 2, 3, 4, is a rather, I think, interesting sort of multi-cyclic compound. Let me make sure I do this right. 1, 2, 3, 4. 1, 2, 3, 4. And in terms of disconnecting this molecule, I'm going to redraw this so that I'm drawing it the exact way the synthesis of distributed enantiomer. Just so that it doesn't get confusing. So I just draw an enantiomer. I'm just going to redraw it so that I'm not changing things up as I. And then methyl group down here. Okay, so this is longifoline. It's a complex, sort of multi-cyclic compound. And as you're starting to think backwards from this and thinking about how you're going to dissect this molecule, Corey sort of discusses in a full subsequent paper, this is actually 1961, to give you an idea of when this took place. He really discussed all the different ways that you could imagine constructing this framework. And there's infinite, for every bond that's in here, you could imagine that might be the first bond that you can go back on. But actually, Corey, in his discussion, discussed specifically 3 of these that stood out for him as potential ways to consider constructing this molecule. And the idea behind this sort of analysis was that let's really, before we head in and really tackle this target, let's really critically evaluate every single route that we might be able to use to generate this molecule. And then let's pick the one that seems like it's going to be the simplest and easy to make. Okay, so Out of the connections that he figured, we'll go ahead and number these just so that we can realize what the bonds are. It's really the bonds around here that we're going to consider first and foremost. So the 3,4 bond. So we're going to have this 1,2 bond here. And we'll sort of look at what, if we break that bond, we'll look at what the carbocyclic structure is. We'll also look at the 2,3 bond. Okay, so we'll break that bond, and we'll look at what that carbocycle is, and then think about how we might make that. And then the other one that he thought was the 3,4 bond that is right here. And so in each of these cases, you're going to see a new cyclic structure, and we'll sort of compare and contrast the different molecules or sort of retrons that would exist in there. So again, you guys have done retrosynthetic analysis in the past. Oftentimes you'll use these sort of retron arrows. Now in Corey's retrosynthetic analyses, and you'll see this with a lot of his sort of proteges, so you'll see it like Phil Barron, for example, and Ryan Shenby, when I saw Ryan Shenby give a talk. Usually when we think of retrosynthetic analysis, we'll sort of leave everything on there. Corey will often just sort of look at the framework and figure, I can always do functional group modifications. It's the carbon bonds that are important. So we'll sort of break it down to at least the molecules. So we'll start with the 1,2 bond. And so sort of flattening this out, what you get if you break the 1,2 bond is a molecule that looks something like this. 7-member ring, so this would be the 1, this would be the 2, and this would be the 3,4. Okay, and I'll just put an X there because, as we'll see, you can put a carbonyl there and you can Wittig at that. That helps give you some idea of some other functional group that might be in there. Okay, and in this case, the bond that we would be making, right, is going to be the 1,2 bond. And so we'll sort of think about how we might be able to construct that 1,2 bond. The other molecule that we might be able to fragment, again, is the 2,3 bond. So if we were to fragment this bond, we would actually get to, I think, a much more, perhaps, complicated looking structure, right? It looks something like this with our dimethyls, 2 position here. Okay, and even just looking at this by itself, so this would be the 2, this would be the 1,2, this would be the 3,4. So we have our methyl group here, but even if you're looking here, right, we're going to have to make that sort of 2,3 bond. And just comparing these two right off the bat, if you were going to have to make one of these carbocyclic structures, which one do you guys think that you would want to pick, just looking at these two? The first one, right? The one on the top, right? You have this bicyclic structure. We can talk about further. We can look at it further in maybe a little bit more detail. But just right off the bat, when you look at these two structures, you see that the sort of the 6-7 ring system here seems like it would be something that would be much more manageable. And so right off the bat, comparing these two, you can sort of at least make that initial intuition that this top molecule might be much easier to make. The last one that he mentions is actually breaking the 3,4 bond here, and that one's actually also not too bad. So I'm going to go ahead and say this one looks way too complicated, right? This looks like it's going to be much easier for us to make. I'm not even going to bother, for the sake of time, we're not even going to bother trying to break that one backwards. But the other molecule that you might imagine making, that you could argue might be similar in level of complexity, would be instead of a 6-7 ring system, you could actually make a 5-8 ring system, right? And so in this case, the bonds that we would be making are 3,4 bonds. Okay, so we're going to try to make that bond disconnection. I think as you're sort of looking at this compound, perhaps this one looks a little bit, perhaps, easier, right? It certainly looks like making a 5-8 ring system might be easier than making this more spirocyclic structure. Certainly you'd have to really break it down more to get a better feel of exactly how you're going to do that. But as it turns out, what Corey ends up doing is he sort of looks at this a little bit further, and certainly this 5-8 ring system on the surface might look at least to the eye, better than the 6-7 ring system. What he sort of thinks about is 8-membered rings, and this is something, when I was doing my graduate work in Mark Snapper's lab, so this is just so you guys get a sense of where state-of-the-art chemistry is. Again, this is 1961. Mark's big project, and this is something like Paul Wender looks at as well. I mean, there's a huge push to make quote-unquote medium-sized rings, right? So even the 7 or 8-membered rings, these are difficult to make, right? And so getting an 8-membered ring or getting a 7-membered ring is going to be a little bit difficult, but what we'll see is that at least the 7-membered ring you could actually make through just a single ring expansion, right? And so it could be the case that what you could do is you might be able to make this molecule from a 6-6 ring structure, right? And perhaps just doing a single ring expansion, right? And so this is the sort of route that he's going to go with. Again, we discussed this last week. I don't know if you guys remember. This 6-6 ring structure here, we've seen it. We saw it last week. Do you guys remember what this is called? Yeah, Whelan-Miescher ketone, right? So this is the Whelan-Miescher ketone. We saw this last week, right? It can be very readily made through Robinson annulation. So in this case, what we see is instead of, the question now becomes, can we potentially take 6-6 ring structures, which we know, convert them into a 6-7 ring structure, and then we're in a position where we could make a sort of carbon-carbon bond here. And again, how exactly we're going to do that, we'll go through in terms of the synthesis. But at least in terms of thinking about how we're going to make this compound, it seems to simplify it fairly quickly, right? We make this bond, we get to the 6-7 ring structure. There's really powerful way, Robinson annulation, to get to this 6-6 ring structure. So that basically means that our strategy is going to involve taking this 6-6 ring structure, and the first method is going to be, well, let's ring expand this to a 7-7 ring structure. We'll make sure that we'll have the functional groups in place as well as we design this, such that then we can subsequently do some type of connection between the 1 and 2 bonds and then get to our core structure of longifolium. Now, as we look at this structure, I just want to go back to this retron that I've shown here. Again, this X group, if that could be, say, for example, a ketone, right? Let's pretend that this is instead a ketone, right? Can you guys identify right away what type of functional group we're going to want to have? Is this carbon here going to likely want to be an electrophile, or is it going to want to be a nucleophile? This carbon? Just in terms of general chemistry, the alpha carbon to a carbonyl. What do we normally think? Right, why?
Well, it's the alpha proton.
Right, so you could imagine taking the alpha proton to a carbonyl, deprotonating it, and turning it into a nucleophile, right? And as we look at a molecule like this, we can imagine that perhaps we could do an intermolecular Michael addition, okay? And so this, in general, again, that just became a Texas carbon, but that's why I put a dotted line there, because what we're going to do, and what we'll see is that you can install that, but what this could come from is an intermolecular Michael addition, where you have an enolate on one side reacting with an alpha-beta unsaturated compound on the other side, okay? So what I'm going to go ahead and do is we're going to discuss this sort of synthesis in a forward sense. So I'm going to erase this in general. But again, the sort of overall idea behind retrosynthetic analysis is you really spend time critically evaluating how you could disconnect the molecule and just try to find the easiest way through which you could do it. And longifolium sort of serves as a multi-cyclic compound where there's all these different bonds that you can do. And again, anytime nowadays you see papers, you'll sort of see this retrosynthetic approach. Usually included within that is the functional groups as well. But yeah, no.
Was Corey the first published retrosynthetic analysis, or what people knew about it?
Yeah, so again, longifolium, it was really 2 papers. Okay, so what came out was the first longifolium paper came out, and it basically said, here's how we did it. It was a sort of standard, just start to finish. This is how we went about synthesizing it. And then he had a subsequent JAX paper that was actually a full article. and he had a much more elongated discussion in that, through which he really discussed all of his different methods. Let me give you the reference for that. So it was a few years later. So the first synthesis came out in 1961, but then the full paper, let me give you the reference because it is a good read, and it's certainly from a synthetic chemistry standpoint. So it was synthesized in 1961, but I think in terms of reading about retrosynthetic analysis, what I would pull you guys to is so E.J. Corey et al., and it's the JAX paper. It actually came out in 1964. The volume is 86, and the page is 478. So again, it's JAX. You can get that just using your graduate center or your Hunter or city account. And again, it sort of has this discussion of all the different disconnections and so forth. So I just sort of provided a very brief overview of some of the different disconnections that he went through, but certainly I could have spent more time breaking down. The paper does discuss that a little bit more. But I'd like to get through the synthesis, talk about some of the chemistry within here, so that we can have some time to also go over the prostaglandin synthesis and hopefully talk about how that led to some other things. So again, you guys know how retrosynthetic analysis, you guys have done this in the past in your, sophomore organic chemistry course. So you know all about retrosynthetic analysis and the idea behind it. I think from a historical perspective, it's important to point out that this 1964, this full JAX paper was the first time that somebody actually laid out the principles and the sort of advantages behind that. So had people been using retrosynthetic analysis beforehand? I don't really know. But this was certainly the first publication where people started to discuss this. And again, we talked about sort of a little funny story about E.J. Corey getting the Nobel Prize just for being really good at chemistry, right? And I think that's sort of true to an extent, but it was actually what he was technically given it for was retrosynthetic analysis. Okay, so again, we discussed how to get to this molecule last week. We know that you can get this asymmetrically even, right, through a asymmetric Robinson annihilation using, you guys remember? Nicole was here. I bussed her for it. She'll be here in 5 minutes. So maybe I'll ask her when she comes in. But it's proline. Remember, it's the proline catalyte, that sort of very first organocatalytic reaction to basically do this intermolecular aldol condensation, right? So it's a Michael followed by an aldol condensation. Okay, so the first thing, and you see this a lot, actually I worked with the Wheelan-Meister ketone when I was a graduate student, and so I ran this exact same reaction. I had a slightly different version of this molecule. But I think one of the first components of this reaction is something that's kind of interesting, right? So you virtually always see this when people are working with Wheelan-Meister ketone. Let me just write it down. I think it's one of the sort of initial, again, I ran this reaction, and the sort of question that always came up is, what's the deal with the selectivity? So it turns out that if you take this molecule and you treat it with ethylene glycol, right, in the presence of an acid, generally toluene sulfonic acid, you can get, you sort of heat this up, it's a dehydrative process, so sometimes you'll throw in a Dean Stark, or sometimes you'll throw in molecular sieves. But what you get is selective acetal protection of this carbonyl over the alpha beta unsaturated carbonyl. Okay? What's that? Oops, I kept doing that because that's the. I apologize if I keep putting a methyl group there. That's actually the one that I made as a graduate student, so I keep putting it there just as a force of habit. Yeah, so we're going to selectively protect, right, the sort of normal ketone over this alpha beta unsaturated ketone. Again, this is more sterically encumbering, so you might imagine that from a steric standpoint, you might protect this one first. But in fact, under these conditions, these acid and ethylene glycol-based conditions, you're going to selectively protect the non sort of enoic carbonyl. Okay, does anybody know why? We haven't really discussed this at all. Does anybody have some intuition or sort of thought as to why this carbonyl might be protected over this other carbonyl over here?
Because the other one is conjugate.
Well, that's kind of a circular argument. So but what about that conjugated system might make it? If this were going to attack that alpha beta unsaturated carbonyl, where do you guys think it might attack?
Will attack on the beta.
Exactly, right? So the LUMO in this system is actually the beta carbon. It turns out that, and I think I'll bring this up really quickly because it's sort of an interesting component of chemistry. I'll ask another question, and I think this is kind of interesting. This is one of the things that I learned in grad school that's always stuck with me. If you took this molecule and you treated it with the same conditions, ethylene glycol and para-toluene sulfonic acid, the product that you actually get out of this, kind of interesting, you actually get that molecule there. So if you try to protect an alpha beta unsaturated enone, what happens is, before you can even protect this, you have to isomerize out of conjugation, right? So that sort of implies that, well, this is the LUMO here, so you need to actually isomerize the double bond before you can even protect it. So if you guys are ever in a situation, say for example in your synthesis project, where you're trying to protect an enone, what you want to use is slightly different conditions. You actually want to use TMS alcohol. This is just something for you guys to know. So you basically, instead of using the alcohol, what you do is you silate the ethylene glycol, okay? And again, I forget if it's the same conditions. I think it's also para-toluene sulfonic acid, but the difference is that you have those alcohols protected. What this does is now the mechanism is going to be slightly different, right? Because instead of the alcohol attacking the carbonyl, what instead happens is the alcohol first serves as a sort of nucleophile to sort of attack into this group, right? And so right, so you get this sort of oxonium species here, okay? And then what happens is now the silyl group can fall off as this then condenses. Okay, so you basically take the ethylene glycol and you turn it from a you turn it from a nucleophilic species into an electrophilic species. So these were sort of conditions. These are, I forgot what these are called. It's like the Japanese term. I can't think of what it was, but these were developed to sort of overcome this limitation. And so again, if you wanted to say, for example, protect this one over the other one, again, an enone is going to be more nucleophilic, right, than just your regular carbonyl, again, because as you can imagine, once that attacks, you have better resonance stability, and so it plays upon this relative nucleophilicity. So anyway, so that's the sort of the one piece of chemistry that I wanted to sort of explain to you guys within the context of this synthesis. Okay, so the next thing that he does is, now that he's protected the one ketone, now he can do some chemistry on the other ketone. So he's got the one protected, he's going to do some chemistry on the other ketone. And what he does is he does a Witte glutination. Okay. This is going to lead to the diene, right? So we're going to get the diene. It turns out that this reaction is non-selective, so there's our wavy methyl group there. He doesn't really care about the stereochemistry at that point. And what he's setting himself up here is, again, the first thing that he's looking to do is he's looking, again, to do this, perform this ring expansion. And the chemistry that he's going to use, again, he's adding an extra carbon here. And then what he's going to try to do is he's going to try to, now he's got that extra carbon out there, he's going to try to promote a sort of a ring expansion. Okay? And so, do you guys remember, maybe this is too out of the box of a question, but do you guys remember, we've seen specific reactions in the past. I don't know if any of you guys, but I'll see if any of you guys remember. If you have an alkene, there's sort of a two-step process that you can potentially use that will promote a sort of a fragmentation. It's a very well-known fragmentation that involves diols. Maybe, right, so the pinnacle rearrangement. So what he's going to do here is he's actually going to promote the ring expansion by using a pinnacle rearrangement. So we'll go through that really quickly. So he takes this molecule and he treats it with, how do you generate a diol? What are some of the conditions that we've learned to make a diol? Arginine tetroxide, right? Pyridine. Again, there's probably better conditions now that can use catalytic arginine tetroxide with a reoxidant. What you're going to get here is sort of a mixture, but he's able to get out the diol. Okay. Now again, we have two alkenes here, right, that he's effectively using, and he's effectively doing the oxidation on one of them. It's not quite clear to me what the relative reason for this selectivity is. My guess is that he probably got a mixture of over-oxidation where he got oxidation here as well. You might imagine, right, that perhaps this carbon is maybe a little bit more nucleophilic, right? Again, because if you attacked from this side, you'd have a carbocation here, and that carbocation could be resonance stabilized by another tertiary carbocation, right? So you could go ahead and draw through that, and you could see that there's this sort of electronic preference. On the flip side, if you did the same chemistry here to lead to a carbocation there, you wouldn't have that resonance stability. Does everybody see that? So there may be an electronic preference for that one alkene. Glenn, you're looking a little confused. You want me to draw that out? So you attack carbocation there, you resonance form from this alkene over, you're going to have another tertiary carbocation. So looking at those two, you can sort of imagine that this alkene would be more nucleophilic based upon those premises, and so that's probably why he got this fairly selectively. But again, the yield is not all that great. It's a several-step process, but I'll sort of mention that it's like 10 to 20% yield over like 3 or 4 steps. So it's unclear how the selectivity was here based upon the paper. But now he's set up for his diol, and so now what he's going to do is he's going to go ahead and promote the pinnacle rearrangement. Okay? And so what he does is he takes his molecule and he treats it with paratoluene sulfonyl chloride with pyridine. Okay? He's going to selectively, in this case, now it's going to be a steric control, right? Paratoluene sulfonic acid is going to react with one of these diols. What we have here is a tertiary alcohol, right? And over here we have a secondary alcohol. So tertiary alcohols are very non-nucleophilic, right? If you think back here, organic chemistry course, you often talk about potassium T-butoxide, or T-butyl potassium T-butoxide as being like this big, bulky, non-nucleophilic base. Again, it's because it's tertiary, right? And the same thing you have here, an alcohol is tertiary. So the secondary, based upon sterics, is going to give you the selective population of that compound. Okay, and now what's going to happen is, again, this is a pinnacle, but it's going to be a slightly different pinnacle, right? If we were to have used, let me just sort of think about this and bring this up really quickly. What's the standard pinnacle rearrangement conditions? You take a diol and you just treat it with acid, right? You just take that diol and you treat it with acid. If we did that in this case, we might not get selectivity, right? Because that proton's going to be much smaller, and so you're not necessarily going to have that same selectivity. You might just as likely be able, in fact, you might more likely be able to protonate this alcohol, and that would leave. But what we want to do is we want to make this the leaving group so that we can promote that ring expansion. Does everybody see that? And so that's why the Tassel That's why he has to basically do this toluene sulfonyl. He has to sort of activate it, not through just acid, but he wants to activate it through making it a good leaving group. Okay, and so that's how he gets the selectivity of the two. At this point, what he does actually, this isn't even isolated. This is just sort of heated up. He'll undergo that pinnacle rearrangement. So if we think about it, we sort of break this down. We look at that carbocation. We can do one of two ring openings, right? We can either do the ring opening from that carbon-carbon, okay? And so if we do, let's say, A, or we can do this one, which would be B. Okay, so I'm going to discuss these very quickly. As I'm redrawing this over here, I want you guys to sort of perhaps think about which one of these two pinnacle rearrangements is going to predominate. Okay, so we've got two potential carbon migrations. We can migrate this one or we can migrate that one for most this ring opening. Okay, now go ahead and I'll draw both of them. Say that this is going to be B. Okay, so if we do the ring opening for B, what we're going to get to is 6-7 ring system. 1, 2, 3, 4, 5, 6, 7. Okay, sometimes when you do this, and I'm going to do it right now because I'm sort of drawing this off the cuff, I'm going to go ahead and number. I'm just going to go ahead and number these just so that I don't screw this up. What we're doing here is we're going to make a bond between the 2 and 4. Okay, so this is 1, 2, 4. Okay, and then 3, 5, 6, and I'll put in everything else. Okay, so we can do that. So the 1, 2, we still got our double bond. The 3, right, is going to have. Wait, I just migrated A. Sorry. Right, I'm making the 2-4 bond. I just did that on accident. Okay, so what we've got here is 4 is going to still have a methyl group coming off there. And here what we're going to have, right, is our carbocation, which is going to be the OH. And again, that would collapse down and get to our carbonyl there. So this is through path A. And if we did path B, instead what we're going to do is we're going to make the 4-5 bond. Okay. Okay, so in this case, what we're going to have is 1, 2, 3 is still going to have the one that's going to have the OH with the carbocation on it. And what we're now making is the 4-5 bond. So that's going to be 4, that's going to be 5, 6, 7. Okay, so we should still have a methyl group at 4. Okay, so again, each of these, maybe if I just redraw them, so this would be the carbocation. I'm just going to go ahead and modify over the top of it because that's obviously going to collapse down. And you're going to end up with one of these two products. Okay? Now, looking at these two, the potential hint might be to sort of look at the product here, right, and see which one of these he wanted, right? So if we look at this compound here, right, we've got sort of the 2, 3, and then carbonyl. Right, so 2, right, so the A fragmentation is the one that he wants. So if you look at the same thing here, right, you've got a methyl group that would be in the wrong position. So clearly this is the rearrangement that he wants. So the question is, and I this is probably fairly obvious, I probably wouldn't have drawn this and gone down this route if it didn't go to this. So perhaps the question is, this is the one that's selective. And the question is why? And he knew that going in, right? He just didn't say, I'm going to do this ring opening, and I'm going to get A and B. He knew that he was going to selectively get A. Why might you guys think this is the case? what's the difference between the two sides? What's the difference between migrating from the 2 bond and migrating from the 5 bond? Right, so sp2 versus sp3. And the fact that it's sp2 in this case, it has pi orbitals, right? And so one of the things that you guys can imagine is that when this bond migrates, right, you get extra participation of those pi bonds, right? And so perhaps the best way to explain this is to think about a slightly alternative mechanism, right, where we have here to help us out a bit. But again, let's imagine a slightly alternative mechanism here. Anybody see Kishore just made a hand gesture? Oh, that was just one. What if we drew a slightly different mechanism? Right? What if we had that alkene? Instead of just a carbocation migration like we think about our standard pinnacle, what if we draw that alkene adding across, right? What if we picture this as the intermediate? Right? And then what can happen? There's participation through that pi bond. Now, is one of these working over the other one? Rick, you look like you're having a... So again, that's not necessarily, this is, again, it's a strange system, which is maybe why Rick's making that face. It doesn't necessarily mean that this is exactly what's going on, but this is helping participate in the mechanism, right? This sort of pi bond participation is helping this process. Now, does it look exactly like this? I don't know. But there might be some element to that mechanism that might assist in helping it expand through the side of the pi bond. So this is sort of an important thing to take note of, okay? We see reactions like where we have similar migrations. We see them in the Baeyer-Villiger oxidation, right? We see them in the pinnacle rearrangement, right? Where you can get migration of one side over the other. Usually what we think about is which bond is going to better stabilize carbocation character, right? And where that can get confusing is when you have sp2 versus sp3, right? Because in that case, it wouldn't really make sense in terms of that stabilizing of carbocation character, right? Because we normally think of a sp2 carbocation as being less stable, right, than an sp3 carbocation. So in those cases, when we're comparing sp2 versus sp3 in terms of what's going to migrate, sp2 will actually migrate preferably. And again, you can go ahead and read a physical organic book to maybe get a more computational description of it, but at least in terms of rationalizing and thinking about it, a mechanism like this, where you actually show the alkene reacting, might at least help you remember which one might migrate best. So whether this is specifically what happens or not, at least it's a way to rationalize it that might help you remember it. Okay. So again, this is what we're gonna get to, and you can see that fairly quickly, what we've gotten to, right, in just a few steps. Again, Wheeler-Mishra ketone is like 2 steps to that compound. Kind of cool. So Wheeler-Mishra ketone, 2 steps to get to this. So really, what we have is 1, 2, 3, 4 steps from a known compound, right? And we're already at our 6-7 ring structure. Okay. So at this stage, all that we need to do, right, is we need to figure out a way to make a bond between this carbon, Now what we need to do is we need to figure out a way to make a bond, right, between this carbon, right, and this carbon. Okay? And as we sort of discussed, we can imagine this being a Michael addition, okay? So what we need to do here is we need to promote a Michael addition between this carbon and that carbon, okay? Now it turns out that the alkene, maybe some of you are scratching your head a little bit at looking at this alkene. If I were to have looked at this, I would have guessed that this alkene probably wouldn't have been there, right? Under these conditions, why might I be kind of curious as to why this alkene is here? I would assume the alkene would already be in that position then.
Yeah.
Why?
Michael addition.
Well, yeah, I mean, that's for the Michael addition, but just in terms of stability reasons, right? If you can have an alkene be in conjugation with another carbonyl, that might be more stable, right? And so we have two factors going on here. But for whatever reason, this is the more stable of the two. And again, Corey actually in the paper discusses this. It wasn't clear that he was expecting this product. But nevertheless, it doesn't matter because we're simply in isomerization away from it. And again, if we can sort of promote that Michael addition, sort of via Le Chatelier's principle, you can imagine a process whereby you could isomerize and subsequently, trap that other isomer through that intermolecular Michael addition. Okay, and so that's what he's going to do here. So he's going to take this molecule. First things first, he's going to deprotect this group. Okay, so again, acetal are deprotected under aqueous acidic conditions. So in this case, he just uses aqueous HCl. Okay, that's going to take off this group here. And during those conditions, what happens is you actually promote the isomerization. Okay, so turns out that the one that we suspected is the one that's more stable. We just got this one, but when he takes this and treats it to the 2 molar HCl solution, he now isomerizes that into the one that we would more likely be expecting to have. Okay, and now it's simply just that Michael addition, right? So it's simply going to be making that bond. So now we have our electrophilic carbon, we have our nucleophilic carbon, we're going to make that carbon-carbon bond, and the way that he promotes this is through the use of ethylene glycol, because he actually has to heat this really high to get this to go. Triethylamine and heat. Now, why might you guys think that heat would be necessary in this process? Why might you guys think that heat might be necessary to facilitate this process? So Larry Scott, who's a mentor for mine from Boston College, makes these big folders, right? And sort of one of the things he always has to do when he makes his bonds is he has to get them really hot. And the reason for that is that sometimes you have to sort of force the molecule to adopt a conformation whereby the bonds can come in close proximity to one another. His chemistry is sort of an extreme example because he's dealing with molecules that would otherwise want to be flat. And so he oftentimes has to go to like 1,000 degrees and use flash vacuum pyrolysis. But in general, oftentimes if you need to sort of force a molecule to adopt a strain conformation where it can react, you oftentimes want to go up to really high heat. And so that's probably the reason why he's using ethylene glycol, because ethylene glycol has a very high boiling point. Okay? So he's effectively refluxing ethylene glycol with a little bit of triethylamine. And that's going to facilitate the Michael addition. Okay? And so what that's going to lead to is this molecule here, right? And so the bond that we just made, so the bond that we just made is this one right here. Okay, so this is the carbon here. This is the Michael acceptor. Okay, so it's adding 1,4. Okay, we're going to get this structure here. Okay, Now, as we look at the difference between this molecule, right, we effectively have our ring system. So let's compare our new structure, right? He's created the architecture. Now the sort of synthesis is now becoming fairly apparent, right? Because he's been able to create this ring system, again, by making that key carbon-carbon that he really spent a lot of time and effort thinking about, is this the best carbon-carbon bond to make? And now he's in a position where he's very close, right? What are the changes that need to be made between this molecule and longifloline? What are the differences? Reduction of this ketone, right? So that ketone has to go away, right? What else do we need to do? So that's one thing we need to do, Nicole. So avidic to this carbonyl, right? So we're going to want to do an olefination here. And what's the only other change that needs to be made? Methylation. Okay. Okay, so if you guys were to think about how to do this, it turns out that he has to use a few more steps because the functional group modification isn't necessarily, you guys just named 3 things. And he's not able to say methylation, Vidic, reduction. He's not able to do that. So he has to spend I think spend a little bit more steps than perhaps he wanted to. But the first thing that he does do is that methylation. Okay, and so again, what he's going to do here is he's going to methylate this carbon. Okay. Now again, this is alpha to a carbonyl, right? So he can make that into an enolate, right, and then trap it with an electrophilic methyl source. Okay, so that's exactly what he's going to do. The base that he uses is this is commonly used. I've never used it, but you see it a lot in the older papers. It's sort of triphenyl methane anion. So he basically uses this and iodomethane, okay, and that's going to get him the methyl group here. Okay, and I have one question for you guys. There's another alpha carbonyl, and this is going to come up a couple times in this synthesis. This isn't the only enolizable carbon in essence, right? There's another alpha proton at another carbonyl, and it's the one down here, right? There's also the one over here, right? So effectively what he does is he exclusively methylates this carbon over this carbon and this carbon. So I wanted to start by just sort of asking you guys, he probably wasn't too worried about this proton here. Why? So everybody, you guys know what Brett's rule is? Now you want to explain what Brett's rule means?
Forming a carbocation at that position.
You mean what?
Carbo.
SP.
Forming an sp3, a carbo anion.
Yeah, no, you're sort of there. So yeah, you couldn't form a carbocation here.
Yeah.
Because that would be sp.
sp2,
hybridized.
And
but we're not talking about carbocation chemistry. But it's the same kind of concept.
Oh.
That's an sp2 carbon.
Yeah.
Right. In our case, we would be deprotonating it, and it would want to enolize.
Yeah.
And so that carbon would be sp2 because of the enolization.
Yeah.
And so you would not be able to undergo resonance stabilization and make that enolate because of Brett's rule, right? Because Brett's rule basically says, and you guys should all be very familiar with Brett's rule, that in certain bicyclic structures, again, depending upon the size of these bicycles, there exists an element of ring strain such that you'll never be able to put sp2 carbons at the bridgehead carbons, right? Because the strain is too high. So again, we always talk about these are things you guys need to know. No Brett's rule, right? So they're not concerned about that one, again, because the enolization is going to lead to an anti-Brett olefin, okay? And then what we have is this carbon versus this carbon. He probably could have figured out conditions to get this carbon if he wanted to, but the conditions that he used were probably what we would say thermodynamic, right? And so from a thermodynamic standpoint, what might make this enolate more stable than this enolate? Something besides nada. What would make this enolate more stable than this enolate? Glenn? More substitution, exactly. So more substitution of an alkene, more stable, right? So that's going to give him the selectivity to get that gem dimethyl group there, okay? So now we've done one of the three things that we want to do. So our next goal is going to be that we need to somehow convert this. Our next two goals, the last two things that we need to do is we need to convert this into an alkene. Again, that should be fine with Wittig, right? And it likely wouldn't isomerize because of Brett's rule, so we're probably good there at some point. But we also need to reduce this, right? But the issue that we have here is we've got two carbonyls, and how do we selectively do chemistry on one of the carbonyls over the other, okay? And what he does is he uses sort of the fact that certain protecting groups, you know, if you were to protect one of these, I'll just sort of draw it and maybe explain as I. But what he does is he takes this molecule and he treats it with ethane dithiene, whatever this is called. And he does this with BF3. Okay? And so these are going to be conditions that are going to allow him to effectively make the dithiene. Okay? Now, if you imagine making a dithiene at this carbonyl, do there seem to be any problems with that? Or maybe I'll ask a different question. If you try to imagine making a dithiene here, might there be problems? And Kishore's nodding his head. So if you're making a dithiene at this carbon, what might be the problem? Right? Imagine just trying to picture that dithiene in that group. You're going to have the sulfur coming up, and you're going to have that carbocyclic structure. Again, you have this group that's coming over the head, huge steric, right? Because you'd basically be trying to put, it's like be trying to put a, you know, like a, I don't know, I was trying to think of an analogy, but I'm not too witty right now. But the thing is that what you're trying to do is you're trying to make a carbocycle there, and that's going to really knock up against this other carbocycle that's right there. So basically what he's used is he's used this group here to protect him from being able to make a dithiene here, and he selectively makes a dithiene at that carbon. Everybody see that? Okay, so that's the first thing he's going to do. What's the other advantage of a dithiene? You've seen dithienes a lot in some of our name reactions that we went over, right? And what are some of the common things that you can do with dithienes? Well, it changes polarity, right, for Umflong type reactivity, right? So dithienes can be Umflong, but that would require a proton here. But one of the other things we've seen with dithienes oftentimes is that they are really easy to then subsequently reduce, right? There are very easy reduction conditions for dithiene. So he's basically put on this dithiene with the expectation that there are many ways, well, I don't know if there were many ways back when he was doing it, but certainly nowadays there's many ways to reduce dithienes. But dithienes are very common intermediate for exhaustive reductions. And so he had likely many methods at his disposal to perhaps get rid of that dithiene altogether and just put two protons there. Okay, so we'll get to that. But meanwhile, now he's protected this. Okay? Which puts him in a situation where now he can simply convert that into a double bond. Okay, so what are the conditions that you guys would probably use if you were going to do a olefination? What would be the first thing that you guys would want to do? Would be the standard way that you take a carbonyl and convert it into an alkene. There's many ways. Wittig. Right? So right away, you might assume that Wittig olefination would be the go-to way to do this. But he can't do that. Why don't you guys think a VIDIG would work in this case? It's the same reason why the dithione was selected. Yeah, a VIDIG is big, it's bulky, right? You'd be effectively, again, you have that dioxirane intermediate, right? Which isn't too different from having a dithione in here. So from a steric standpoint, you can't use a VIDIG, right? For many of the same reasons that the dithione couldn't go on there, or it was selected against it. So he doesn't do a VIDIG, okay? So instead he goes with, I think, smaller chemistry. He does, simply does, whoa. This thing that I have has like they forgot to delete a proton, so there's like a Texas carbon. What he does is he wants to take this and he wants to effectively reduce it, but what he's going to do is he is going to just take it and treat it with methyl iodide. Okay, he's going to take it, he's going to treat it with methyl iodide, and then he's going to subsequently take that alcohol and he's going to undergo an elimination. Okay. The problem with that, and so that's going to be his strategy going forward. The problem with that is, I don't know, that's not what he ends up doing. So there must be a reason why he can't simply add iodomethane here and then do the elimination. And one of the reasons might be is that the subsequent processes for reduction might give him problems in the presence of an alkene, right? You could imagine that maybe a sodium type reduction of this dithione and you had an alkene there, you might not really want that. So it gets a little steppy here, and so I'll just sort of take you through it, and it's not clear. Again, in any synthesis, you might have the way that you want to do it, and then you sort of can't do it, and you have to figure out a way around it. So the last few steps in this get a little bit steppy, and so I'll just sort of walk you guys through what he does. Certainly not the most elegant, compared to how quickly he built up all this other complexity. The NPM isn't necessarily all that elegant. What he does to finish this molecule is he protects this carbonyl. He does a lithium aluminum hydride reduction. Okay, so I'm just going to sort of go through these steps fairly quickly so that we can get to prostaglandin and sort of finish this up. So what he's going to do is he's going to just treat this with lithium aluminum hydride. That's going to reduce this. Okay, and then what he's going to do is that once it's reduced, then he's able to actually reduce off the dithione. Okay. So the conditions that he uses are, I think, are kind of interesting. So he uses sodium and hydrazine. So when you guys see those conditions, what reaction might quickly come out in your mind? One of the main reactions that we discussed. Well, birch would be a reduction of like an aromatic, so certainly sodium metal. But what's going to happen if you take an alcohol in the presence of sodium? Right, you're probably gonna, because again, that's going to be the alcohol following the LH reduction. You're probably going to, sodium's going to react with that and generate the alkoxide, right? So you'll effectively have the sodium alkoxide there. So I wouldn't worry too much about the sodium doing single electron chemistry too much. But it's more the hydrazine. Again, we're trying to do an exhaustive reduction. And in what conditions that use hydrazine, again, we usually see this with a carbonyl. That's why I was kind of, when I saw this, I kind of scratched my head a little bit in terms of why these were the conditions that we chose to do. But where have we seen exhaustive reductions? Wolff-Kishner, right? So Wolff-Kishner is an exhaustive reduction of carbonyls in the presence of hydrazine. And so it's not clear to me exactly how this specific reaction is working mechanistically, but it could be the case that under these conditions, the dithione sort of comes off and it's displaced with the hydrazine, or it could be some other single electron-based mechanism. It's not entirely sure to me the mechanism through which this chemistry is taking place. But nevertheless, these are the conditions that he uses, and they're very Wolff-Kishner-like, to reduce the dithione. So that's going to get rid of the dithione and put in its place 2 protons, right? And then what he's going to do is he's going to oxidize back up. So for whatever reason, again, it's not entirely clear to me. It's not entirely clear what some of the limitations around why he had to do this were. But again, he sort of effectively protects the carbonyl, again, because the hydrazine, right, if he tried to do these conditions on the carbonyl, what's going to happen? You might end up reducing the carbonyl, right? So he effectively, you can at least think of this as he reduces the carbonyl to protect it from the Wolff-Kishner, right? He does the Wolff-Kishner, and then he oxidizes it back up. So it's kind of an interesting, usually we think of protecting groups as being like ketals or being like PBS groups or so forth. But in this case, he protects the carbonyl by converting it to an alcohol, and then he oxidizes the alcohol back up when he's all done. It's kind of weird thinking about the alcohol being a protected version, but it's just because of the conditions that he was using. He didn't want a carbonyl around there. Okay? So again, that's going to get him to the molecule, with the exception of the last thing he needs to do is he needs to just convert this into an alkene. And so again, what he's going to do here is, as I made the comment before, is he probably tried lots of things. He probably tried the Wittig olefination. Maybe he tried, I don't know if Peterson olefination was available at this time. Actually, I wonder if the Wittig was even, this is 1961. I'm trying to think when the Wittig was discovered. The Nobel Prize for Wittig was the same time as H.C. Brown's, which was, I think, in like 1980. So it's possible that Wittig wasn't even available at this time. So anyway, what he does is he does methyl lithium addition into the carbonyl, and then what he does is SOCl2 and pyridine. And so what that does is he's going to make the alcohol, then he's going to chlorinate the alcohol and just promote an elimination. And that's going to get him to the total synthesis. Okay, so I think it's a nice example. Again, Corey has many, many examples of total syntheses, and you can read through many of them. Longifolene, I think, is a very concise, synthesis. This is actually probably significantly shorter than the strychnine synthesis that we saw. Could be argued that maybe strychnine is a little bit more complex, so it might require more steps. But I think, again, the important part of this is that this was, in terms of retrosynthesis, the reason why I sort of discussed this one, is this was the first example of a synthesis where was the first example and the first time where retrosynthesis was sort of invoked as an explanation through which to consider constructing a molecule. And again, particularly up to the bicycle, again, you look at the end game. The end game isn't, in terms of the functional group modifications, it might be a little bit steppy because there's back and forth between different groups. You have this protection, deprotection, and so forth. But how quickly he went from this molecule to this molecule in particular, I think is pretty impressive. And again, I think the way that the reason why that happened is that they were looking at this bicycle and trying to think of, this is the complex part of this, right? What's the best way that we can go about making it? And he really spent a lot of time thinking about all the different ways to go about it. And so specifically from the Wieland-Miescher ketone to this, it's very efficient. And I think it's sort of a, it highlights, and it highlighted at the time, the value of really thinking about all the different infinite ways that molecules could be synthesized. So anyway, so there's been, since this synthesis of longifolene, many others have come up with their syntheses as well. There's been, like, for example, Thiel's older approaches where you can imagine doing two bonds at the same time to construct that architecture. But what you see is in many of the syntheses, they do sort of focus on that sort of 1-2 bond disconnection that I showed there. So many of the other syntheses that have subsequently come out have used that same strategy to synthesize the molecule. So again, this is longifolene.
Can I ask you a question?
Yes, you can.
So it's a natural product. It comes from some creature or something?
Yeah, so what do you guys, anybody have any ideas of what kind of natural product this is? It's an all-carbon structure. And in fact, in his paper, there's nothing too special about this compound in terms of biological activity or anything like that. But it is a specific type of natural product. And in Corey's discussion on this, he effectively says that this class of molecules are among the biggest challenges to synthetic chemists in part. And we'll discuss this a little bit more in terms of biomimetic cascades processes. But yeah, the terpenes. Right. So again, terpenes come from, terpenes are particularly, we often think of terpenes as being from wood and things like pinene, right, and things that are coming from wood, but they're everywhere. I mean, terpenes are very common, and so anytime you have these big carbon molecules, right, where you have many different disconnections. We'll discuss this actually a little bit more in the context of biomimetic cascades, but there's really neat biomimetic processes which go about making these.
So my next question is that enzymes figured out how to do this
Yeah.
bizarre chemistry, right?
Mhm.
All this,
Mhm.
high temperature conditions, strong reductants,
Yeah.
everything, but in the cell, this is all done within a.
Yes. Yeah. So, and again, and Rick is pointing to, I think, Rick is pointing out one of the real, I think, sort of frontiers of chemistry now, right, is sort of enzymes are so efficient. And so we're going to talk about biomimetic cascades and how you can imagine looking at how a biomimetic process might lead to molecules very quickly, but as Rick points out, very often that's due to an enzyme, right? And the fact that a molecule might be forced to adopt a specific conformation within that enzyme that's favorable such that it brings those together, right? So it doesn't require going to refluxing ethylene glycol. The problem with enzymes, on the flip side, right, is that enzymes are very specific. And so when you're trying to develop new chemistry, that's really what Corey, and that's, I think, Corey's, other chemists do it as well, but I think Corey has historically done it better than anybody else. Let's make a target, and we'll use that target to sort of highlight, and we'll talk about this a little bit within the context of prostaglandins, what are some of these limitations and how might we be able to come up with better ways to make them. And so there have been biomimetic processes towards these molecules. I'm not prepared to discuss them, but they certainly invoke, I think in the biomimetic process that has been done, they actually, I forget exactly the whole process, but it's like a huge carbocycle. I forget, it's like the biggest one that you could imagine out of this whole system, and there's like a tube. Really neat. But yeah, I mean, I think that you see a lot of people nowadays, specifically organometallic chemists, I think it's exciting. Like they try to harness that specific power of enzymes to potentially make chemistry better. But again, the problem is that usually when you make a synthetic method, you want it to be fairly broadly applicable. And so where you see, I think, biology coming in, maybe we can discuss this because we got that extra last day of class, so maybe I can discuss this a little bit, is the sort of hybrid approach to sort of harness biology, harness the powers of biology, being able to get you to specific intermediates, and then try to finish them up. And I think the best example of that is, well, a couple of them. Taxol, right? So people have figured out ways to take yeast and get yeast to create large forms of late-stage synthetic intermediates of Taxol. So they'll make all the complex components of Taxol, and then they'll sort of finish it up. And the big one nowadays is actually Jay Kiesling, right? So did you guys see Chrissy's talk on artemisinin? Yeah. Okay, so none of you guys weren't here, but artemisinin is this natural product that's anti-malarial that's sort of like the last line of defense for malaria. The problem is that malaria is super complex. The sort of natural product source is kind of rather expensive to be able to treat, especially people like in the areas where malaria is the biggest problem, right? And so there was this sort of big push to try to come up with a really cheap way to make artemisinin. And what Jay Kiesling has done is he's done a similar thing. Let's harness biology. We already know that this target is powerful. Let's use biology to try to make it as efficiently as possible. And again, it's the same thing with like Taxol. He's come up with a way to make not necessarily artemisinin, but like a precursor that's only like 1 or 2 steps away. And so, yeah, that's stuff that's being done a lot more lately. But again, this is 1961. I think that the real push in much of his work was to figure out ways to make them, and I don't know that they necessarily understood these biological processes as well. But nowadays, and that maybe that'll be what I do with that extra day. I haven't quite decided what I'm going to do with that extra day that we have, but maybe I'll discuss that on that extra day. But yeah, certainly that's, I think, highlights how nature is way better than us at certain things. But again, you know, a lot of the methods that we have, we want them to be more general, and sometimes enzymes are too specific, so that we can't use them for lots of different reasons. Okay, so anyway, so here's longipholine. And again, I think it's historically it's very significant, and from a point of retrosynthetic analysis, and then again, I think there's some interesting chemistry that we've been able to discuss. For example, the selective acylation is something you guys should the selective ketal formation over here, I think is one thing that you guys should probably learn from this chemistry. The other thing is the sort of migration, again, sp2 and sort of alkene participation to help the selective migration is another thing that you guys should pick up from this. And those are probably the two big things of chemistry. And then now that Nicole's here, she can tell us how the wheeling ester ketone is made asymmetrically. Proline. Right. So proline catalyzed, effectively aldol condensation, the desymmetrization. So here, that being the carbonyl, one on the other. Okay. All right. All right. So the next target that I'm going to talk about for the next hour or so. Does anybody need to use the bathroom or anything? Yeah, 5 minutes. 5 minutes. Yeah, or whatever. Head to the bathroom. And that gives you an opportunity to be here for 3.5 hours. Yeah.
We're talking about prostaglandins now?
Uh-huh.
Okay.
Yeah. Prostaglandins.
Starting from what?
Starting from cyclohexadiene, cyclopentadiene. So, yeah, he makes like a whole series of them, and so it's just sort of like, there's a couple reasons, like there's 2 reactions that are like Victoria's famous for, that his first synthesis sort of show, you know, he's like, it's a deal holder, and he first has to do it racemically, but then he later comes out with he develops an anti-selective diazole to sort of overcome that process, and then there's also like a reduction that sort of leads him to develop an asymmetric reduction, which is why I'm sort of discussing the process synthesis. So, not from arachidonic acid. Yeah, no problem. I'll see you at faculty meeting.
Yep.
David's not coming, obviously.
Yeah. Is she sick?
She's taking Princeton, New York Airport.
What?
Sorry. Was I supposed to do that?
Princeton to New York. Oh.
She has to take her parents to New York Airport.
Oh.
Yeah. Oh my gosh, I'm sorry, I was late.
It's okay.
Yeah.
It's okay. I was telling everybody and I don't know if you were here. But Nicole wasn't. I'm actually videotaping this,
Oh, cool.
so you
We
can.
can have this at a video.
So what I'll do is I'll put it up on YouTube and probably just. I don't know if I want to make it like. I don't know if I want to make it as available to like everyone. What I might do is I think there's some way to like password protect it or something.
Yeah, I think.
I did this for my undergraduates, and
You watch your videos with them.
yeah, it's nice, but it's also kind of. It can be a little embarrassing.
Don't worry about it. Yeah, they're good videos, they're helpful. It makes you look good, it's not like, it's not good.
Yeah, except that, except that occasionally when you make a bonehead mistake, and then suddenly all the students are like, what an idiot. It's like, I'm human. Not you guys, not most of the students, but the few that like to complain about you, just because you teach organic chemistry and half the class fails.
You have to go to rate my professor. To like, let them what?
I mean, you can't, I try not to. The problem is this. The problem is this, is that anytime that there's no Morellis, there are like no Morellis. And so anytime like I'm looking for, like whenever I go to my old papers, like I'll just go through Google. Instead of having to like dig it up, I'll just go to Google, I'll just put in my name, I'll just put in my last name, and because there's no Morellis, my group website is the first thing that pops up, and so I just use that to go into my publication. So like I'm always like, that's how if I have to bring up an older publication or look back at old stuff info, I'm always going in there. Problem is the moment you do that, like right below it is ratemyprofessor.com, and so it's like right there staring you in the face. Right. So, I mean, it's, I think that it's good to know the criticism, especially when you're new at it like I am, because then you can learn from the criticism. But I think on the flip side, you know, they can be pretty nasty. Yeah. And again, it's much better. The problem with rate my professor is that you're very likely to just the people that are going to spend the time to go and log in and make comments about you on it,
Yeah.
like they're either going to be people that hated you or they're going to be people that really like you, and so there's not going to be anything in between. Nobody that's just sort of like is going to go in and do that. The much more we have in CUNY, they do more of like, and you guys will have to fill these out. They do the, I'm sure you've done them, like you fill out the evaluations.
Yeah.
Those are so much more informative because then you get like, like when I teach 200 students, I have like 120 different comments. You know what I mean? So at that point, then you can sort of look through them and you can see, this represents the majority of students. So again, you get a few, just like on Rate My Professor, you can sort of pick it out. Like you get a few that are like, greatest professor ever, and then you get a few that are like, worst professor ever. So you get those two, but then, and you can sort of like just be like, okay, and then just focus on the sort of people in the middle and just say, okay, these are the sort of the normal students and what do they have to say. And again, I think it's much better to look through those to get a sense. Or there's like half and half. So like, yeah, the department, the dean. I think there's one that's specific for you, the department, the dean, and that's for like evaluating you in the future. Then there's the ones that are like open to everybody.
There's a difference between those evaluations, the ones that are those ones that are online.
So there's ones that like you could read of all the different faculty,
Yeah.
but then we also get another
Oh, okay.
set of data and comments. And those comments, only the professor, like the department head, and like, the dean and stuff, I think, are able to see. So those are more, well, no, those are just, nobody's going to read them. So I think that students might be more honest. Yeah. So anyways, okay, so we've got about a little over an hour to go through prostaglandins. Okay, so again, longifloline, I think, is certainly it's a really nice synthesis. Again, it was 1961. You can start to see, I think, when you look at the quinine synthesis, which was done about 20 years prior, quinine itself was a difficult molecule, but the sort of the formal synthesis that sort of Woodward did, I would argue, isn't really all that complex, right? Specifically when you then compare it to what he did with strychnine. So what you start seeing, right, is around this time, right, really 50s, 60s, and then carrying through the 70s and 80s, the molecules just start to become beasts, right? And so longifloline, by today's standard, might not seem too complex, but certainly at the time, it represented the sort of terpene family of natural products, fairly complex all-carbon molecule, and so it's cool from a synthesis standpoint, but again, then from a historical standpoint, the fact that he had that sort of 1964 subsequent full article where he discussed the sort of ideas behind retrosynthetic analysis really are what make longifloline historically, I think, a very significant synthesis and one that I thought that I would bring up. Okay. The next, again, Corey's arguably made more contributions to synthetic chemistry than anyone else. Maybe Woodward might have, maybe the argument to be made that Woodward matched him, but certainly Woodward died young and Corey's into his 90s and was still kicking out, still doing amazing work today. So, just the sort of breadth of which Corey has done has led to numerous targets, and I considered a lot of them, some of them that I think highlight, the level of complexity that synthetic chemists have been able to achieve in total syntheses. The one of the ones that sort of I can't think of the name of it. But anyways, there's been many that are much more complicated than the ones that I'm going to talk about today. But yeah,
Did Woodward die because of smoking?
I think so. I think it was like lung cancer. So yeah, but it was definitely an untimely death for sure. He could have done a lot more in his life. But anyway, he did a lot in the time that he had. So anyway, so as I was trying to decide what I knew that I wanted to do longifolium, and when I was sort of deciding what other targeted Cories that I wanted to do, I thought that I would pick a molecule that he's synthesized that I think highlights, again, this idea that synthesis can sort of really highlight the limits of our technology, right? And so, Corey can dissect a molecule and come up, especially through the retrosynthetic analysis, he can certainly dissect how to construct a molecule as best as good as anybody. And through that, he can often look at, well, this is the best way that we're going to do that. Do I have to develop chemistry to help me get through these, right? And so there's been a lot of synthetic developments in Corey's work that have really been inspired by his synthesis. And so I'm trying to think, was it a Barron group meeting or one of them? Somebody had a classics in Corey TL that you can find. He would have all these little TL papers that would be, oh, in the context of this, we discovered this little thing, and they end up being huge deals. Tetlet, Tetlet, yeah. Because Tetlet back in the day was like the Orglet nowadays, except that Orglet now requires a lot more stringent characterization and everything like that. But the thing with Tetlet is that it didn't require as much characterization and everything else. The whole point of it was get things out. What have you found out that's new? Let's get it out quick so that people can have that. And so Corey has tons of really good work that was just here we discovered this thing, we want to get it out there while we continue working on our syntheses. And so he would just sort of, they would make some discovery within total synthesis or make some chemical method development and just publish that, get it out really quick in TL. So there's a lot of nice work within there. But anyway, the prostaglandins, I think, are one that, especially even given some of the name reactions that we've seen, I think it's a shorter synthesis. It might not be as complex as some of the other targets that he's made, but I think it sort of highlights we'll go through it and we'll discuss two of the big limitations in the synthesis that he came up with, and then we'll see subsequently how he developed new synthetic chemistry to sort of overcome these limitations. And I thought this was a good way to do that in the context of this sort of synthesis. Okay, so prostaglandins. Does anybody know what prostaglandins are? So I'll go ahead and draw structures. Anybody heard of prostaglandins? So prostaglandins are, yeah.
Does this have something to do with that pathway with aspirin?
Yeah. I mean, you're on the right track. So prostaglandins are inflammation sort of signaling molecules that are synthesized by arachidonic acid. So arachidonic acid is a sort of a very lipid-like molecule, and then it can be converted into all these different molecules, prostaglandins, leukotrienes, thromboxanes, many of which mediate different cell signaling pathways. What you're thinking about is COX inhibitors, right? So cyclooxygenase is one of the first steps towards many of these prostaglandins. So it inhibits an enzyme that takes arachidonic acid and converts it into this other intermediate that then subsequently goes on to generate these. So prostaglandins are one of the inflammatory signaling molecules. And so you're sort of inhibiting the formation of these through the inhibition of that pathway. Okay, so I'm just going to show one of them, just again, because the point is, given the time that we have, I want to get through the synthesis, and then I want to discuss a couple of the limitations of that synthesis, and then we'll discuss how that sort of led him and maybe perhaps inspired him to develop chemistry to overcome these limitations. Okay, so this is an example of one of the prostaglandins. Actually, there's several different versions of them, but this is just PGF2 alpha. I forget if it's like more significant than some of the others, but again, the prostaglandins in general are inflammatory signaling molecules. So this is one of them. Some of the things about it, it's fairly rich in stereochemistry, right? So it's got 5 stereogenic centers. The ones that are going to be key to this synthesis are these ones in here. The one that's here, as we'll see, is done really not all that selectively, which then leads, as we'll see, to the X reduction. The way to sort of reduce alcohol selectively. But what's going to happen in this synthesis is you're going to see 2 things. Again, as you look at this molecule, you know, and sort of looking at this retrosynthetically, what we're going to see is we sort of have these 2 alkenes, right? These are going to be done through Wittig-like chemistry, so this is going to be through Wittig. This one's going to actually be done through a Horner-Wadsworth-Emmons olefination. Again, as we'll see, you can imagine that being a alpha-beta unsaturated carbonyl, so that would lead to the Z alkene, whereas a non-selective Wittig would lead to the, stabilized would lead to the E, opposite. The sort of non-stabilized would lead to the Z, right? So we discussed the selectivity of Wittig chemistry a little bit. When we sort of break this back, that sort of leads to molecules that, at least formally, we can picture like looking something like okay, formally lead to something that looks like this, okay? Right, again, because these would be the 2 carbonyls, right? As we're going to see, this could then come from, this could equal, effectively, like sort of tautomeric hemiacetal-acetal forms, right? So again, that can sort of wrap around and form the hemiacetal. As we'll see, that will allow them to perhaps protect this, right, and have that be, say, for example, a carbonyl, right? So you can protect, imagine this tied back, and in fact being that carbonyl itself, okay? And then from here, what we're going to see is that this molecule itself is going to come from so what we're doing here, right, is that we are, let me make sure I get this right. He's going to effectively use this that 5-5 ring system. Okay, so 5-5 ring systems always want to be cis to one another, right? And so effectively what he's going to do is he's going to use this stereochemistry here to set this stereochemistry there. Okay, I'll also draw this a little bit more in line with targets that we're actually making now. Okay. Okay. So again, you can imagine like a lactinization there. You could set that stereochemistry. Okay. And then from this molecule, he's going to effectively set all the stereochemistry together. But what he's going to do is imagine this now tied back to the other side. Okay, so if you can imagine right? This sort of ring structure here. So what I've done is I've tied this back on that acyl group and made a lactone. Can you see that? Okay. This is going to come from right, that's going behind it. This is going to come from this molecule here. Okay, and then what he's going to do is he's effectively going to do as we'll see sort of Diels-Alder chemistry. Okay, so what's happening is we're going to break the molecule. If we sort of just look at the overall picture here, what he sort of recognizes is he wants to basically take these alkenes, right, as the point through which we're going to put on those longer appendages, okay, through Wittig and Horner-Ross's Emmons chemistry. He then realizes that this carbonyl could be wrapped around and made into this sort of 5-5 ring system. Again, the reason for that is really to help establish the stereochemistry here from here, right? So to basically use this stereocenter to relay this stereocenter because the 5-5 ring system is going to want to be cis, okay? And so we have that sort of alkene there, and again, as we'll see, he'll do a lactonization through an iodolactonization process. And then that's also sort of tied back with this other alcohol, which is this now lactone, which as we'll see, that could then come from this molecule through a Baeyer-Villiger oxidation, right, to sort of oxidize that to that, install that oxygen there, right? And then what we're going to see is it's not exactly this Diels-Alder, but he's going to effectively set this ring system there for Diels-Alder chemistry. And so, again, it's this sort of relay of stereochemistry within the synthesis that's, I think, pretty remarkable in how he sort of, there's 4 stereogenic centers around here, and he's able to do that diastereoselectively. So again, we'll see that this one had some stereochemistry issues, but it's really the sort of construction of these 4 contiguous stereocenters that really kind of makes this synthesis pretty nice. And again, this is I think 1969. So is that right? Let me double check. Okay, yes, it's 1969. Okay, so anyway, so we'll go through the synthesis, and then I'll try to highlight the things that I think are sort of important in this. So again, the sort of Diels-Alder that's going to be done is going to involve this sort of cyclopentadiene there. Okay, and so what he's going to do is he's going to take cyclopentadiene, okay? Cyclopentadiene can be a little bit difficult to work with, right? You have to like crack it because it will actually be Diels-Alder very quickly. What he does is he takes this and he deprotonates very readily with sodium hydride and then takes mom chloride. So methyl put on the sort of put on the methyl ether there. Okay, so do you guys know, what would you guys expect just right off the bat? So what he's doing is he's going to deprotonate this carbon and he's going to attack it with that electrophile. So what do you guys know about the pKa of like just allyl protons, Lewis protons? They're relatively acidic, but certainly not that acidic, right? Not so acidic that you could deprotonate them with sodium hydride, right? Usually we think sodium hydride is like deprotonating alcohols, right? Like, which have pKa's of like 15. I don't know what the pKa of an allyl proton is, but I would guess it would be in like the 30s, right? So you would assume that you would need chemistry, at the very least an ammonium, like LDA or something like that. Perhaps even stronger, you might need like butyllithium or something like that. But in this case, he's able to get away with simply using sodium hydride. Does anybody know why? Conjugation, yes, in a way. What were you saying? Right, it's the fully, right, so the moment that you deprotonate this, right, exactly, you become aromatic. Right, so if any of you guys end up working with cyclopentenyl ligands for metals or whatever, you can generate them fairly quickly again because this is aromatic. Right, 6-phi electrocyclic system, okay? And then what he does is, this is a sort of a classic way to have a ketene equivalent in Diels-Alder chemistry. You see this used quite frequently if you are just trying to get ketene chemistry. What happens here is he does a Diels-Alder reaction between this compound and this compound, and that leads him to this bicyclic structure here. Okay. Now, what's critical about this reaction, right? Yeah.
I'm sorry, I have two questions.
Yeah.
The first one is, why did he collectively get that
That's not chiral.
the second one?
Yeah, it's not chiral. I drew stereochemistry there. I just showed it to you before, but it's not chiral.
Oh.
Yeah, because look, it's symmetric. Yeah, so it's symmetric, so it's not. But this will come up later on. So this is racemic. So that's going to be one of the developments that we'll discuss later on.
Second question,
Mhm.
my second question is, could we just use dicyanide, with the Diels-Alder, the diaminoxide?
This?
Yeah, because this has been like two cyanides to get the exclusively one cyanide.
Well, it doesn't matter. You're going to see it doesn't matter. Could that have been the case? Yes, but this is one of the things, is that this molecule, as we'll see, is commonly used for, as a way to, as a surrogate for carbonyls. So this group, you'll see this time and time again, these chloro nitriles are commonly used. You can convert that into a ketone. So we'll see. So this is chemistry that you see not too infrequently. Like this is effectively where this is effectively used as like an equivalent of ketene. Okay. Okay. So anyway, so the stereochemistry here doesn't matter. It's a mixture at that point. But what he does here is he takes this, and again, as I was just saying, you can actually hydrolyze this in the presence of KOH, water, DMSO. Okay, and I think what happens here, I'm not entirely sure, but I believe what happens here is, I don't know the mechanism of this, but I think it's simply just, again, I'm saying this, that I could be wrong. I think that all that happens here is that water, you displace the chloride with the water, okay? Again, I'm not 100% sure. And then what happens is this just collapses and you lose cyanide, right? So I think this is what happens, but I could be wrong. But at least in terms of mechanism, that at least is somewhat rational. Okay. So the point is that now you're at this sort of ketone here. That's the one that we discussed here, right? And then what he's going to do is he's going to do an MCPDA oxidation, right? So this is where we have, right? This is a Baeyer-Villiger oxidation, right? And he selectively oxidizes he effectively oxidizes specifically this carbon-carbon bond. Okay. So again, why is that the carbon, when he treats this to MCPDA, why does the oxidation go there? We just discussed this earlier a little bit. Somebody maybe else. So why? So we could either oxidize and put an oxygen in this carbon-carbon bond or that carbon-carbon bond. But Baeyer-Villiger usually goes, we just said one thing that it can do is it can go where you have the alkene participation. But other times what will happen is it'll move with the one that's what? Yeah, the more stable carbocation is the one that's going to actually migrate. So we're going to see insertion into that carbon-carbon bond at that side. Okay? Okay. So at this point now he can hydrolyze this molecule. Okay? And at this point we can open up the ring and maybe start making it look a little bit like this guy here. Okay, so we've hydrolyzed it, and now, again, the Diels-Alder, followed by the Baeyer-Villiger, followed by the hydrolysis, has led us to a diastereoselective process where we now have 3 stereocenters set in terms of what we want. Okay, so that's the important part here. So the Diels-Alder was effectively used to really set 3 stereocenters at the same time, right? Because you have the 2 coming up, again, the methoxy is going to want to be away from everything else because of sterics, and so that Diels-Alder has really been the important part of this. It's set effectively 3 stereogenic centers simultaneously, okay, and has allowed us to get to this structure here. So it's a really, again, Diels-Alder is, you know, when you guys can use Diels-Alders, it can be a really powerful way to set stereochemistry, to make carbon-carbon bonds, and I think this is a really good sort of example of that. Okay, so now what he wants to do, again, as I stated earlier, is he's going to use this stereocenter to set this stereocenter, right? So he's going to want that oxygen there, right, which is going to effectively become this oxygen. And the way that he does this is through an iodolactonization. Okay, so again, you've probably done similar chemistry in undergraduate labs, with just iodide, not actually run it, but at least talked about it in the course of your talks. They use this Ki3, which is a sort of a version of iodide, buffers it with sodium carbonate. Okay, and what happens here is you get to the iodolactonization. So what's going to happen here is we're going to just think about this as an iodolactonization. Okay, so we're going to make the, you can imagine this as being the iodo, the sort of the 3-membered iodonium bridge, and then the carboxylate or the carboxylic acid adding in, and then subsequently getting, or this would probably be deprotonated before it actually happens, so it would be the carboxylate. But that's going to set the stereochemistry at that center. Okay, so you've got now this iodide. Okay, so again, that iodide is just there. And what he does here is he simply, start on the rest of the board here. What he's going to do is he doesn't really need that iodide there. Again, you don't want that iodide there. So what he does is he just sort of reduces it off using radical-based processes. So he uses like AIDN and tributyl ammonium hydride, right? And so just sort of generate the radical and quench it with the hydrogen. But before he does that, he doesn't want the alcohol giving him problems. So he's going to want to protect the alcohol eventually anyway. So he first acylates it. So he's going to acylate this alcohol with just acetic anhydride, pyridine, right? And then he's going to subsequently do that AIDN, tributyl ammonium, or sorry, tributyl tin hydride. Okay, and what that's going to lead to is this intermediate here. Now, this intermediate, okay, so I'll redraw it over here. Okay, so the intermediate that I've drawn over there is often referred to as So this intermediate here is fairly significant. So I'm going to show you guys the synthesis of one prostaglandin, but Corey is actually synthesized like a whole ton of them, a whole bunch of them. And oftentimes this is the intermediate that he uses for all of them. So this has actually been named the Corey lactone. Oftentimes, if you ever hear the Corey lactone, this is what people are referring to. So again, it's this 5-member ring. Yeah.
Before the protection of the alcohol,
Mhm.
what is stopping the hydroxyl group because it's in a very good conformation to eliminate the iodine, forming the epoxide, and the iodine coming in on the other side, switching the iodine to the.
Well, So Nana's basically saying, what's to stop this from getting deprotonated and then adding in? I mean, it's possible that they only use one equivalent of bicarb. I don't know. I'd have to look at the specific details of it. But if they just used one equivalent of this, then it would all get quenched by this, right? And then what's left over is I-, and that's not going to be strong enough to deprotonate the alcohol. So that's my guess. But if you had an excess of bicarb, it might actually do that, like you said. But I'm not really sure. So anyway, so this is Corey's lactone. This is the Corey lactone. And again, it was used for a series of prostaglandins. What it is, in a way, is it provides you with this sort of stereochemistry where you have 4 contiguous stereogenic centers all around this 5-member ring. And so again, it has that sort of value because many of the prostaglandins have the same sort of stereochemistry around this region here. Okay, so for the sake of Corey's synthesis of this molecule, again, what we need to do is we do a Horner-Wadsworth dimezolination and then a Wittig. Okay? And so the first thing that he's going to do is he's going to simply take this molecule, he's going to demethylate this group here. When I say simply, it's kind of remarkable. BBr3 is sometimes be cruddy to work with. But BBr3, 0 degrees Celsius, you actually get a 90% yield. So he's going to demethylate this group with boron tribromide, using boron. Sorry, he's going to demethylate this with boron tribromide. And then what he's going to do is he's going to oxidize up with basically PCC. Glenn, can you do you have your laptop out? Hey, look at PCC real quick. Because I think Corey might have developed PCC.
Primitive Christian Church.
Pyridinium chlorochromate. Because as I'm like drawing this, it's not really saying. It's like this is not PCC per se, but I think it's like a PCC. Yeah, the idea is that again, what PCC really is, right? Is you got to remember that. So Corey developed it. What year? Is there a paper down at the bottom? Accidentally discovered it? Yeah, as I was like drawing this, I was like, wait a second. Corey is. Okay, so that's actually this predates PCC, but it's the same type of reagent. So he was probably doing similar type of chemistry development. So anyway, so this is sort of PCC like in a way. Again, what PCC is, if you guys just remember it, it's really just a soluble, an organic solvent soluble chromate source that you can try to keep dry, right? So the only reason Jones reagent goes all the way to the carboxyl or to the carboxylic acid, right, is that you have water, which then makes a hydrate, and then that hydride gets oxidized. So what PCC is it's just an organic soluble chromate source that you can use to oxidize selectively to the aldehyde. So, but yeah, as I was writing this, I was like, I think Corey developed PCC. But, it's one of many things. Okay, so what he's going to do is he's going to get to this aldehyde, okay? And then what he's going to do is he's going to do the Horner-Wadsworth dimezolination, and he's going to get this sort of side chain, except that that's going to be oxidized. So The Horner-Wadsworth-Emmons reagent that he uses is going to be one, two, three, four. One, two, three, four. Is going to be that one. Okay, so this is going to be the Horner-Wadsworth-Emmons reagent that he uses. Again, Horner-Wadsworth-Emmons gives the E alkenes, right? And so what's going to happen here is that we're going to get side chain okay, so we're going to have that side chain, okay? And then what you can do here, right, so this is just done with sodium hydride. Okay. He's going to get to that compound, right? And then what he's going to do is he's going to reduce this compound, okay? So he's just going to take this molecule, he's going to treat it with zinc. Sort of hydroborating, kind of very similar, right? Zinc borohydride, right? So it's kind of similar to sodium borohydride, right? That is zinc. And what he's going to get is now I got to be careful when I talk about this a little bit because again, as I'm sort of up here writing, sometimes I think of things that I'm not entirely sure of. Okay, but what do you notice about that reduction? Right, so it's the zinc borohydride, and I'm wondering, I don't know when sodium borohydride was invented, but if you were to run this reaction based upon what you guys learned from your name reactions, what conditions would you use? So let's pretend that we didn't know that zinc borohydride led to this product, right? And let's pretend that sodium borohydride didn't work out so hot for us, right? Because what's the problem with sodium borohydride, perhaps with an enone? Yeah, you might get a lot, right? So you might get a lot of beta addition of the sodium borohydride as well. What are the conditions that you guys, again, if you're ever up against a situation where you want to reduce the carbonyl of an alpha beta unsaturated carbonyl, what are the conditions? One of the main reactions that you guys learned. Involves sodium borohydride or a borohydride. Loosh conditions, right? So it's a cerium trichloride, forget, methanol. It's some cerium and methanol, and then sodium borohydride or something like that. But it's one of your name reactions. So you guys want to consider this reduction. You have to recognize this is an enone. And so if you're planning on your syntheses or you ever want to do your syntheses, you don't just want to do standard sodium borohydride. You probably want to use Loosh conditions because, again, it makes it a little bit harder and it makes it add this sort of carbonyl there. Okay? The problem here is that he gets a 1-to-1 ER. So he gets the sort of the alpha and beta epimers at this position. As you might imagine, that's going to be another sort of limitation that we're going to discuss, right? And again, in terms of the CBS reduction, we'll sort of discuss how that sort of played out there. Okay. So anyway, so this is the this is getting very close to the final molecule, right? All that we have to do, in a way, is we have to take this group here and effectively make that the sort of partner for the Vidic, okay? And then we effectively have our end game. And so, we effectively have the molecule made. So again, we'll have to at some point take off that acyl group at some point, but then again, we'll have our free alcohol up here. And again, this could be the sort of the carbonyl through which we do Vidic olefination on, okay? So the chemistry that's going to require is doesn't work that great, or they don't want to do some of this chemistry with a free alcohol. And again, you see this from time and time again, sort of having to modify protecting groups and so on and so forth. And so The protecting group, and again, you've got the acyl group on there, and you probably don't want that when you're going to be trying to reduce this group here, because it might lead to side products. So he's going to put on a different protecting group. So what he's going to do is he's going to just switch up the protecting group. So he's going to take off the acyl group. That's going to be done with K-carb and methanol. Okay. Now, one of the things about this is that you might look at this and you might say, wait a second, wouldn't that also hydrolyze the lactone? But one of the things you guys have to realize is that lactones, especially 5-membered ring lactones, are very fast to form. So you might hydrolyze it and it might just snap back shut. So I actually had a friend during my postdoc that was trying to isolate these compounds where she had an alcohol at one place and like a carboxylate at the other, or methyl ester at the other, and she just could not ever isolate that compound because it was always just lactonized, form of lactone. So this probably does hydrolyze, but then it might just shut back down. So the lactone survives, but they're able to deacylate this. And then what he's going to do is he's going to put on a different protecting group, one that's going to be less likely to undergo the reductive conditions that are going to be necessary to sort of take this group off. And so what he puts on is a different protecting group that some of you may be familiar with, others you might not be. So he's going to use DHP and toluene sulfonic acid. Okay, what DHP is that compound here. Okay, so what's going to happen is you're going to deacylate, and then you're going to effectively put on this THP protecting group. Okay, just tetrahydro. What's that? Pyran, yeah. So it's dihydropyran. You're going to turn it to tetrahydropyran. Thank you. Don't want to blank there. Okay, so it's going to become THP. Again, that's just the hydro, it's just the amount of hydrogens around there. So what's going to happen is the group is going to be, I'll draw it out on this one. So it's just going to be a protecting group just like that. Okay, so just an acetal-based protecting group. I'll just break that one down. And then for this, I'll just abbreviate it as DHP. Okay. And I completely run out of board space. Should put this further that way because I might have actually been able to complete this. Okay. So what he's going to do here, actually, I can do this fairly quickly. Maybe I'll just, given the time, I'll sort of take you guys through it in a two-step sequence. So what's going to happen here, right, is that now that these groups are protected, he's going to take this molecule and he's going to treat it to dibol. Okay, it's the diisobutyl aluminum hydride, right? What that's going to do is it's going to reduce this down to the aldehyde. Okay, so you can imagine this being, again, we sort of discussed this relative polymerization before, but really what it is it's this aldehyde. Okay, so effectively at that point we're going to be at that aldehyde. Now again, this aldehyde isn't a major compound. Again, we discussed earlier, we sort of showed the tautomeric forms where it can exist as just the sort of hemiacetal up here, right? And these are sort of back and forth, and so the hemiacetal is going to predominate. But again, you have enough of this aldehyde, sort of via Le Chatelier's principle, that what you're going to do is you're simply going to take this and you're going to treat it with Wittig conditions. And so the Wittig salt you're going to use is going to be this. Okay, and then the second step is just removal of the tetrahydro. H2O. Okay, so all you're going to do is you're going to do Wittig olefinations on this, then you're going to take off the THP groups, and that's going to lead to the sort of natural product. Okay, so again, this is a fairly short, I think, synthesis. You know, it's a nice synthesis. You know, if we look at a total step count, starting from cyclopentadiene, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16-ish. So 16 steps isn't too bad. The molecule has 5 stereogenic centers. And again, this is 1969, so we didn't quite have the level of technology that we had. Again, highlighting in this method, I think, is the stereochemical control that this has. So again, here's this sort of Diels-Alder-based method. Again, it's this Diels-Alder that you're really setting 3 stereogenic centers out of 4, right? And then you're able to relay the 1 stereo center to create the 4th stereochemistry. There's this 4th stereo center. So again, that's the sort of the good things about the synthesis. But again, in any Cori synthesis, what you're dealing with is, again, it's highlighting some of the really good things that we have about chemistry and some of the good things that we know. And sort of I just highlighted those, right? Diels-Alder chemistry is a really effective way to set stereochemistry. This sort of idea that 5-5 ring systems can be used to sort of control stereochemistry at this step. These are all really good things about the chemistry. But there's 2 things that are rather bad about this chemistry. Now again, it's 1969. I don't mean this should not be coming across as, again, it's just the limitations of the chemical methods at the time. And the 2 really bad things are, first of all, this is a racemic synthesis. Now, what Cori was able to do to make it an antioselective synthesis is that he was able to take, this intermediate right here. Okay? So this intermediate here, you could actually resolve it using ephedrine. Okay, so if you take ephedrine, you can basically co-crystallize out one enantiomer and leave the other enantiomer behind. So you could sort of separate the 2 enantiomers and you could use either one to sort of get to the natural product. Okay. The problem with that method is what? You're losing 50% of your enantiomer. Okay, so you're effectively, just because of that non-selective nature, in addition to the potential loss in material through the resolution, you're going to be left with a crummy, you're really going to take a big whack in terms of the yield there. And the other reaction, right, is this fluorohydride reduction. Again, it's non-selective, so you're getting, at best, 50% yield, right? And you're likely to be getting significantly less. And so these 2 processes, both the Diels-Alder reaction and this reduction, I think, are 2 examples that sort of illustrate some of the limitations of the chemistry of the time. Okay. Now, E.J. Cori has developed a lot of synthetic methods. And again, we just talked about PCC as an example of one that is widely used, that Cori developed, final protecting groups, and so on and so forth. But in terms of stereoselective processes, one of the things that that we've seen in the past in sort of our main reactions, right, is that Cori has really leveraged this idea of catalyst control, and the sort of catalyst that he's used a lot, we saw within the context of sort of CVS reductions. So I just want to first talk about his development of an asymmetric Diels-Alder reaction, and then I'll discuss the CVS reaction, which we sort of discussed already. So Diels-Alder I'll go through a little bit more time on because we haven't really discussed Cori's asymmetric Diels-Alder. And then if we have time, I'll discuss the CVS reduction as well. Okay, so the chemistry that Cori developed for an asymmetric Diels-Alder reaction can be slightly different, but you'll see it'll get to the same product. Okay, so he's going to have a benzyl group there rather than the sort of methoxy group. He's going to take this, he's going to treat it with this alpha bromo acrolein. Okay. And in this reaction, he is going to use the following catalyst. I'll just draw this over here. Okay, so here we have an amino acid derived catalyst. This is derived from tryptophan, right? So this is a tryptophan based chiral catalyst, where effectively all he's done is he's taken tryptophan and he's treated with borane to make this new Lewis acid, okay? And it turns out that this is a Lewis acid that can actually catalyze this Diels-Alder reaction. So if you simply use 5 mole% of this reagent, you get is diester selective process. Red is getting dead. So what's happening here is that this is activated. You're effectively activating the carbonyl. Okay, so it's Lewis acid activation. This is terribly drawn. Okay, but what's going to happen here is, and this is sort of difficult to see perhaps, but this is a common element in Corey's chemistry. Sort of see it, I think, in the CBS reduction as well. Maybe that'll be more steric based. But this sort of idea, and this was developed within the context of like, sort of got this idea from a lot of the work that had been done on, sorry, lecturing for 3 hours is kind of exhausting. Sort of idea of when you have chiral auxiliaries. Remember we talked about chiral auxiliaries that are groups that you put on and take off. There were certain chiral auxiliaries that had these longer aromatic groups. And it was reasoned that a lot of pi stacking interactions could really help facilitate the organization of transition state intermediates that would be beneficial. And so you'll often see in a lot of Corey's catalysts that will have sort of aromatic groups that can often help participate in organization through pi stacking. So what you've got here is that you have this sort of indole, right? And unlike normal reactions, or like you might think about certain reactions where there's a steric component, right, where maybe you don't want this group up there. In this case, what the group is actually doing is you're getting like effectively secondary orbital interactions between the pi system of that tryptophan. That's helping, you're effectively bringing this in here in a sort of chiral environment. You've got sort of pi-pi stacking between these two. And it sort of holds it into a conformation where then this group has to come in, and it really only has one way that it can sort of come into this system, right? So what that leads to is an asymmetric process where you get this product here is 92% EE. Okay, so it gets like a small amount of the endo version as well. Don't ask me why this sort of endo is minor. You know, again, based upon what you guys know about Diels-Alder reactions, generally it's the endo one that's formed. I was actually scrambling to try and figure out why the endo one wasn't forming in this case, and I couldn't find it in time. So maybe I'll mention it next week if I have time. But anyways, they get the exo. And then, again, what they're really trying to do is they're trying to get this to a carbonyl, and so he's able to do that in just a few steps. What he does is he effectively takes this aldehyde and converts it to these conditions hydrolyze the bromide and also make the the hydroxylamine, and that's going to get you to. Okay, and now as we start to look at our compound here, right, we're starting to look very similar, right? We've got a hydroxyl now at the one position, and we have what's effectively in the same oxidation state as the cyanide, right? So if you can imagine just eliminating water, you have the CN bonds there, right? So that CN, you just eliminate water, and you have this CN. And so that's what he does. He just basically takes this and he treats it with calcium chloride and some pyridine, and that affects the elimination here. And then so what you end up with is right, and then he just treats that with the same conditions that we saw previously, like sodium hydroxide, right? So sodium hydroxide, and that's going to get him to the same intermediate. So it's sort of a formal. So it's sort of a formal synthesis of this is formal asymmetric process. So he basically uses this asymmetric Diels-Alder reaction, and admittedly, he's not able to use the exact same dienophile, but he's able to use an alternative dienophile, which gets him to the same product anyway. Okay. So that's the Corey asymmetric Diels-Alder. You actually see it a lot. He had a synthesis, I remember it came out when I was in graduate school, of Tamiflu. You guys know what Tamiflu is? So there was like this big, like probably 10 years ago, 10, 15 years ago, there was this big, like, the swine flu, or I forget exactly which one it was. It was one of the avian bird flu virus outbreak or something like that. Everybody was scared about it. And one of the big things was like, we need Tamiflu, we need Tamiflu. And that's another example of where he used a similar sort of Diels-Alder-based catalyst in the sort of synthesis of Tamiflu. So again, that's sort of the circular process of how chemistry can be used to identify problems, right? Like where things need to get developed, and then subsequently those new methods can then be used in synthesis again, and that's what you sort of see with the work of Corey, is that he'll very often use synthesis as a way to identify limitations and develop new methods around that. I think given the time, I'm just, it's been a while since I've had to talk for this long and stand up here.
Was that like stressful in being here? Or did I
Rick? No. Yeah, no, that's just.
The first semester, like
Yeah.
all the 3 classes, you never had people coming in.
Yeah, no, I mean, if,
Who's the only one who would have? Was it O'Brien? Who was pretty new? The other two,
Oh,
they
only-
had been teaching
only
for like
because of-
10 years.
Only if you knew those people coming.
yeah, you have to do it up until you have tenure. Actually, it's a PSC CUNY policy. So anyway, let me just finish that, and then I'll turn off my video, and we can talk about whatever. But the thing is that you know, I'm not going to bother talking about CBS catalyst because we already discussed the CBS reaction. I was going to discuss it, but I think we already went over CBS when we discussed. That's one of our name reactions, so you guys have already gone over that. But again, CBS reduction was made in part because there was no good way to do that chemistry, right? The stereochemistry of where that reduction is was so far away from where you could potentially be able to use diastereoselective processes, right? And so he was able to set all these other stereocenters, but there was no way for him to set the stereochemistry of that one alcohol. And so he just had to make it in a 1-to-1 ratio and separate the two. CBS catalyst thus allowed him to actually develop that. And kind of interestingly enough, I won't get a chance to talk about it, but when I was in graduate school, one of my friends there, a couple of my friends actually, were working on a similar class of molecules called isoprostanes. And they had developed, actually a person who developed it before I showed up, had developed a synthetic method where he basically made, he didn't worry about the fact that it wasn't enantiomerically pure. His goal was he wanted to make this entire library of isoprostanes. There's like 8 of them. They were all the different stereochemical outcomes of them. And what they actually did was they made the molecule racemically, but again, they wanted all the isoprostanes. They wanted them all because they wanted to do biological testing to figure out was one more important biologically than the other, so they wanted the whole library. So what they did was they made the racemic molecule, and then they did the CBS reduction, and then they got a mixture of diastereomers, and they were able to then separate the 2 diastereomers, which also then thus helped resolve the enantiomers as well. So it's kind of a neat little way. And again, if you don't care about, if you're just trying to make a specific one molecule, then you don't really want to do that. If you want one selectively, and then as it turned out, they found that one of them looked a little bit like had a lot more activity than some of the others. So a friend of mine went ahead and came up with an asymmetric synthesis of that chemistry, and they had developed some interesting chemistry within that context. So again, that's all we're going to talk about today with Corey. You know, you guys will come across, it's just important to recognize that you're going to come across so much chemistry that he sort of did, and I think in terms of the interplay between total synthesis and synthetic methods development, and how you can be inspired to develop new synthetic methods based upon limitations discovered through total synthesis, is I think really a hallmark of Corey's work, and I think it's worth mentioning. We will be discussing biomimetic syntheses, I think, next week. It's important to recognize, again, Corey had his hands in a lot of different things. I won't discuss, but Corey also had a big hand in biomimetic syntheses as well. But I figured we'd have a whole day full of Corey, so I'll talk about some of the other people who actually are more focused on biomimetic synthesis, and some of the examples that I really like. So anyway, so I think we have the exam next week, and then we'll talk a little bit about biomimetic syntheses as well. So, okay, I'm going to turn this off and